Hello, y'all. Today we're going to be talking about the aldol condensation. And what we mean by the aldol condensation is that we can take two of some kind of ketone or aldehyde, specifically only those two. And let's say we react it with some base. Well, if we react this with some base, what we can get is we can actually attach, well, we use twice of this, so we can attach two of these together right over here. And so attach two of these together and make this aldol. So ald meaning this aldehyde, and this all meaning this alcohol at the very beginning. Now this will be our initial product, but the thing is this can react even further. And so if we add some kind of heat and some kind of heat, and we do a base catalyzed elimination, this will be explained in the mechanism. If we do that, we can actually get this thing called an alpha beta unsaturated product. Now, what do I mean by alpha beta? Well, we have to count the number of carbons away from our carbonyl. And so what this means is that this is an alpha right here. This is the beta carbon, as it's 2 carbons away from the carbonyl. And this is unsaturated because there's a double bond. Now, there's one other thing I want to stress about just the scope of this reaction right here. Right? If we use 2 of these acetaldehydes, so this H and then there's an extra methyl group right here. We use 2 of them, we essentially only have 4 carbons in this case, right? Looking over at the initial product, our aldol product, we only get 4 carbons. Again, 1, 2, 3, 4. Heck, we can even look at our alpha beta unsaturated product. Well, we still only have 1, 2, 3, 4 carbons. Now, this is very important because unlike most of the other reactions we learned this quarter, all of these reactions from here don't lose any carbon. It changes, the number of H's and the different types of bonds, but it never loses carbon. So that's what I want you to think about when we start looking at some of the other problems. Okay, so now we should actually look at the actual mechanism, how this even reacts in itself. So our first step in almost all these reactions is we have to make the enolate. So what we can do is take off this H using an AOH, move these down and move this double bond onto the O. And we've essentially made our enolate. However, this enolate, again, is very nucleophilic. So these electrons on the double bond can go ahead and attack the carbonyl of this carbon right here. And then just stabilize that, we can move this double bond to make a new double bond right here. Now, if we make a new bond right here, we have to break a bond or else carbon will have 5 bonds somehow. So we have to break this, move it on to the O. From there, we do a nucleophilic attack, which is what this entire step was. What we get is this almost finished product. We've made this new bond between here, here, and here. And so that's how you should be looking at this reaction from there. We make that new bond and, well, we still have the negative charge, so all we have to do is just do some aqueous workup and we get our initial product. So that's great. That's pretty good. We can, but we can keep reacting this further, as we showed in the last slide, right? So we need to make our enolate again. So instead of taking this OH, what we can do is take this H right over here. Take out that H, make a new double bond, move this over onto there, right? Okay, so we get to this negatively charged product, which is what we expect after we do an enolate. But instead of reprotoning it like we did here in the aqueous workup, we can do a base catalyzed elimination. What does that mean? Well, we can move these electrons back down to make the double bond. We can move this double bond to make a new double bond right over here between this carbon and this carbon. And then we can just pop off this OH as it is, as an OH minus. Now, this can only be done if you add heat to this reaction. And we can cut off that OH, and what we get is this new double bond right over here, and the OH as a final product. Now, the OH will just pop off, but this right here is the alpha beta unsaturated species that we get. And so this is how we can do this entire reaction, but let's look again at the new bonds we made. The new bond we made in the first step is between each other, right over here. And then the second bond that we made is that double bond. So keep those bonds in mind and we can see how this can be applied in further reactions. Now, if I were to tell you to give me the original ketones from this molecule right here, or the original carbonyls from this, how would we go about that? Well, in all these, first we have to identify your alpha beta carbonyl, or your C double bond O for layman's terms, right? Well, we found it right over here. It's going to be in the middle because we have our carbonyl. We go alpha to it. Well, there's part of the double bond, and then over here is your beta. So this will be your alpha beta carbonyl. Okay, so how can we get back to our original product? Well, the first step we need to do is we need to cut this double bond right in the middle, right in the center. And what we can get is get these little species from right here. And so get this double bond. And so we get this. Essentially, we cut it in half. Now, looking at these two carbons between here and here, we need to replace them with certain bonds. For the carbon, the beta carbon in this case, or the one that's farthest away from your C double bond O, we give that an O right here. And so one of our products, or one of our original reactants in this case, since we're doing a reverse reaction, will be this aldehyde right over here. We just add an O onto whatever the squiggly line was right. Now, looking at our alpha carbon, right, this one right here, instead of adding a single O, we add two H's. And so what we get from that is this CH3 right there. And make sure that there's the double bond onto that O. And note, because there is an extra H right over here. So when we add the two H's, it makes a CH3 group right over there. So these are the two carbonyls that will get to this product if we do an aldol reaction. So that's one strategy of how you could actually view going in reverse reaction. Okay, so let's look at our first practice problem right here. So what it's asking us is we have to both show the beta hydroxyketone, or the C double bond O and the OH, the aldol product, and the alpha beta unsaturated ketone. Well, from these two products. So how can we actually show that? Well, first case, we need to find out what makes the enolate, right? And so in order to find out what makes the enolate, we have to check which one has any alpha hydrogens. Well, if we look at our left product right here, we go alpha to it right there. Well, the problem is there's no hydrogens. So this can't be the enolate. Looking over at our right product, well, shoot, we have two H's right over here that we can deprotonate. And so this is going to be what's going to be making our new bond right here to this carbon right here. And so when you're looking at it, your nucleophile will keep the C double bond O, but your electrophile, or whatever is being attacked, that's going to turn to the OH. And so looking at this, wherever we make this new bond, we have to make it from this carbon all the way to this one right here. Because this one can deprotonate, and this one can attack, and this can attack the electrophile, or this aldehyde right here. So how would that actually look like? Well, our beta hydroxyketone would look a combination of the two. So remember, we have to have our benzene ring, and then remember, this is going to be your electrophile, because that's what's getting the electrons from here. This one right here is going to be a nucleophile, so that's what's going to be getting, making the new bond. Now, if it's the electrophile, what we do is we make whatever that C double bond O was into an OH. Okay, that's dandy and all, but okay, what's our new bond? Well, our new bond is going to be to that C double bond O, and that was attached to an H right there. Well, the thing is, we're still missing carbons at the very end. So how do we do that? Well, if we count our carbons from where this attacked, this would be 1, 2, and 3. So wherever we had on this product, because 2 and 3 did not react, we still have to add those two right there. And then just for counting sake, this would be 1, this would be 2, this would be 3. So this is one of our products. This is our beta hydroxyketone. But now it's also asking us for our alpha beta unsaturated ketone. So how did we go about that? Well, looking back at what we've done in the previous reactions, in order to make that alpha beta unsaturated ketone, we cut off the OH, and we make a new double bond between carbon 1 right here and this second one. And that's because we have to do this base catalyzed reaction. So looking at our final product, we have to cut off the OH, so that's not going to be there. But what replaces it is a new double bond. Okay, well, that's fine and dandy. We still have carbon 1, 2, 3, and we still have that C double bond O H at the very end. And just to keep in mind where these carbons are, this will be carbon 1, 2, and 3. Looking at the differences, we cut off the OH right here, and we added a new double bond. And so this will be our final product and the answer to this problem right here. Okay, so this is where we start going to reverse reactions right over here. And so it's asking us, what were the original reactants that created the product? Now, if we can recognize this, this is our aldol. Well, why would that be an aldol? Well, we have some kind of C double bond O, and we have some kind of OH. Okay, so but what were the two original reactants? Well, okay, so this is only after the first step. Because it's the aldol, this will be the second step of the aldol reaction, or initial product. Now, how do we go about turning this about? Well, remember, whatever our nucleophile was, that's going to keep the C double bond O. And whatever the electrophile was, that's going to be an OH. It's going to turn that C double bond O into an OH. Well, let's try and find these specific parts in our molecule. Well, okay, so good, we found our nucleophile. So it will be between this C double bond O, whatever's attached here, and whatever's attached through here. And so this part will be our nucleophile. But how can we recognize our electrophile? Well, that's our OH. So it's going to be here, and the rest of this molecule will be the rest of the electrophile. Now we have to make a new bond. So this new bond has to be made between our nucleophile and our electrophile. But right here, this is the only bond that connects the two, right here. And so we're going to have to cut this bond right here. Now, going backwards, well, remember, our C double bond O, that turned into an OH. So we have to turn this OH back into a C double bond O for our original product. So taking out the H, adding a double bond O, one of our original reactants is going to be this. So this sort of aldehyde with the C double bond O right here. That's going to be our electrophile. Now, what is our nucleophile? Well, we just keep the C double bond O, but we just have to break this bond. And so what we get right there, this will be our nucleophile. And so that's how you can retrosynthetically look at an aldol reaction and even decide to go backwards to try and find out what bonds you made. So keep those different things in mind, and we will see you next.